First one we did already. Kind of. And in case I haven't said it, you can have this chart in the front of your book for the test. There's no way I am expecting you to memorize this. Ain't gonna happen. I clearly don't have it memorized. So yeah, this chart you can use. All right, so we have a negative 1/3 sine of 2t. That's my first part. That next one's a cosine, right? And the k is equal to 1. So we've got 2 cosine of t, 2 cosine of t. And that last one is a sine. And k is equal to 1, so that means I don't have to worry about anything else in the numerator, and I can just go with a plus 5/3 sine of t. So that's my answer that I end up with. Negative 1/3 sine of 2t plus 2 cosine t plus 5/3 sine of t. Give me again, help me out, thumbs up, thumbs down if that one makes sense. Thumbs up on that one, we're good, cool, thank you. Thank you for being willing to play my thumbs up game, I appreciate it. This is figuring out what works for class. Okay, any questions on that one before we do, and class is gonna be a little shorter today, I think, and that's okay. Any questions on that one before we do a result that's going to make it easier for us to do step number 3? Anybody, anything, questions there? Okay, let's come up with this result then. So once again, this result is intended to make it easier for us to find an inverse transform. And we're gonna get a bunch of these results as we keep going throughout the chapter. Here's the first one. So result, I'm never gonna remember what number we're on, but that's okay. So result number 1 for finding the inverse Laplace transform of capital X of S. You can label these, you can help me remember what number we're on because like I said, I'm not going to remember. So result number 1, here is what this theorem says, and we're gonna state it in 2 different directions. First of all, the Laplace transform of the integral from 0 to little t of f of, and now I can't use little t anymore because I've used it in the limit, so I need to come up with another letter. We're gonna go Greek, so f of tau d tau is equal to, we'll do this in just a sec, but let me get you having that written down first. The Laplace transform of the integral from 0 to t of f of tau d tau, and you can use whatever letter inside of there you want, is equal to capital F of S over S. The Laplace transform of the integral from 0 to t of f of tau d tau is capital F of S over S. And you might be saying, Dr. Meyer, we were supposed to be finding results for finding the inverse transform. How does this possibly help us? Because of part number 2. What we can say if we go backwards is that the inverse Laplace transform of capital F of S over S is the stuff inside the parentheses on the left-hand side. Integral from 0 to little t, f of tau d tau. That's the part that's more useful, the second part there. Basically, this is what's going on. So you want to integrate once for each, I'm going to say extra s that you have in the denominator. I'm going to integrate once for each extra s that you have in the denominator. What this lets us do is integrals instead of partial fractions. That's what's going on too, or that's what's going on here. So you can integrate once for each extra s that you have in the denominator instead of using partial fractions. can integrate once for each extra s that you have in the denominator instead of using partial fractions. That's why this result is nice, assuming that you have a function that easily integrates. It's just a way to not have to do partial fractions. If you like partial fractions, you can still do that, that's fine. But this is a way to not have to use partial fractions. Jason, question.
So does that mean for like, say you have like s squared, does that mean that there's 2 extra s's?
Exactly, and that's going to be the second example that we do. We're going to start with an easy one first with just one s, but if there's an s squared, then there are 2 extra s's, and then you have to integrate twice. So hang on just a minute, fantastic question. That's going to be the second example that I do. Other people, other questions? Otherwise, we've got 2 examples that I want to show you with these. Something else? Okay, let's look at an easy example first, and then we'll look at one with more s's in the denominator. So, for example, how about this one? We're just jumping into the middle of the problem here. So let's say that I get to the point where capital X of s is 1 over s times s plus 3. So I'm totally jumping into the middle of the problem. We've done step 1, we've done step 2. Everybody's clear on where we're at. We've done step 1, we've done step 2. Okay. So in this case, there is 1 extra s. So we want to integrate once. The question is, what do we integrate? What's the function that we want to integrate? And the function that we want to integrate is the inverse transform of what's left, 1 over s plus 3. The stuff without any of the extra s's in it. So look in the front of your book. What is the inverse transform of 1 over s plus 3? What's my transform? Inverse transform of 1 over s plus 3. Look in your book, look on your screen, whatever you need. What do you got? Inverse transform of 1 over s plus 3. Be brave, volunteer, raise your hand. What do you got? Zach, go ahead.
E to negative 3t.
Absolutely. So what I'm looking to integrate, this is e to the negative 3t. And so therefore, capital X of s, the thing that I'm trying to find, is the integral from 0 to t, e to the negative 3 tau d tau. Remember that I have to change my variable in the integral because t is in the limits. And if I have t in the limits and in the integral, that gets super confusing. So I have to integrate once. Integral from 0 to little t, e to the negative 3 tau d tau. Okay, that means I need a negative 1/3 out in front, e to the negative 3 tau, evaluated from 0 to little t. Remember how you find an antiderivative of e's. And then I just need to plug in and subtract. So negative 1/3 e to the negative 3t minus negative 1/3 e to the 0. So final answer ends up being negative 1/3 e to the negative 3t plus 1/3. So no partial fractions. We didn't have to do any partial fractions for this one. That's great. That's fantastic. All we had to do was integrate, since there's 1 extra s in the bottom. All right. Questions on that one before we do one more with 2 extra s's? Stuart, question. No, you're good?
That was
okay. Are we good? Thumbs up with that example? We're happy? Yes, we got it? Cool. Okay, let's do one with Jason's example where we have 2 extra s's in the denominator. So again, we're jumping into the middle of the problem. Here we go. Capital X of s is 1 over s squared times s squared plus 1. So that's my capital X of s. 1 over s squared times s squared plus 1. And in this case, we need to integrate twice. There are 2 extra s's in the bottom. There's an s squared, so therefore I need to integrate twice. Question is, what am I integrating? So I need the inverse Laplace transform of 1 over s squared plus 1. That's what I'm going to integrate twice. Front of the book, table, whatever you need, go find the inverse transform of that and figure out what we are going to need to integrate twice. What's my inverse transform of that going to be? You should be getting familiar with some of these, hopefully, especially as you're doing your homework also. So this one has s squared in the bottom, it has a constant in the top. That is a sine k is equal to 1, and so this is just sine of t. Okay? Please, 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 please don't get bad with the notation and write down both of your integrals at the same time. We're going to do this in steps. We're going to do it once and then we're going to do it again. We are not writing two integral signs next to each other. That will make me very, very crabby. Don't do that, please. So once and then again. That also means that I can't just write down little x of t equals because I've got to integrate twice. So we're just not going to label stuff. And we're going to go with integral from 0 to little t sine of tau d tau. That's my first integral. That's my intermediate step. That's not equal to anything. And I am not putting another integral out in front. We're just going to do this twice. Okay. You should be able to do that. Do that integral, see what you get, and then we'll do it one more time. So integrate gives you a negative cosine. We plug in 0, we plug in t. Negative cosine of t plus 1, or I flipped the order around, 1 minus cosine t, so that I could just have the positive out in front. 1 minus cosine t. Tell me we're good with 1 minus cosine t. First up, 1 minus cosine t. Okay, this is my second integral, so now I can label this, and this is going to be my little x of t. Integral from 0 to t, 1 minus cosine tau d tau. Don't forget to switch your variable. You never ever, it is bad form and very confusing to have the same letter in the limits as inside the integral. Don't do that. That's the reason we're switching your letter. If you don't want to use tau, you don't have to. You can use any letter that you want, but don't switch, don't use the same letter. Make sure to switch. Okay, evaluate this one and see what you're gonna get. And the integral of 1 is not t, not in this case. So once you integrate, once you plug in, should get t minus sine of t. The second part totally goes to 0. T minus sine of t. Have you caught up? Are we good? Thumbs up. T minus sine of t. Thumbs up. Cool. So notice what we did. We had no partial fractions that we had to deal with at all in this case. If you wanted to, you totally could have done it with partial fractions. So I'm not going to do this, but we could set it up. We could also say that 1 over s squared times s squared plus 1 is as plus b over s squared plus cs plus d over s squared plus 1. We totally could have done it that way. You could have done partial fractions. You could have solved for a, b, c, and d. And then you could have gone through and done your inverse Laplace transforms that way. I personally would rather integrate than do partial fractions, so I am going to integrate, but you could do it either way, whichever way you want. Okay, questions on that? Anybody, anything? What do we have for questions? Stuart?
So I'm just wondering, even though the bottom is like s squared times s squared plus 1, how do we know that we have to integrate twice and not 3 times? Because technically aren't there like there's 3 extra s's?
So the only extra s's that we think about are s's that show up by themselves. That's the s squared at this point. So that's the thing that tells us that we have to integrate twice. If we had an s cubed, we could do this and we'd have to integrate 3 times.
So if it was like s times s squared plus 1 times s squared plus 4, you'd only do it for the s, right?
Right. So I won't
Okay.
work through, yeah, so I won't work through this example, but that's a good question. So sometimes you will have to mix this with partial fractions. So if you have capital X of s is 1 over like s plus 1, s plus 4, then you can integrate once because there's an extra s. And the question is, what do we want to integrate? That's going to be the inverse transform of 1 over s plus 1 times s plus 4, and you're still going to need partial fractions for that one. So sometimes you do have to mix this technique with partial fractions, and sometimes honestly it is going to be easier to use partial fractions. It's up to you. You can do whichever way you want. Sometimes this one's easier, sometimes partial fractions is easier. It just depends on how many s's you have and what you need to integrate. So sometimes you might have to mix techniques too. Other questions? Other ones that you have?
Thank you.
Here? Anybody else? Okay, I am going to stop sharing my screen with you. So here's my plan for the rest of class, just for a little bit. I want to give you just a little bit of time to talk about homework problems, etc. So I'm going to divide you up into breakout rooms in your homework groups. You don't have to stay very long, but I just want to give you a natural place to kind of check in, see where you are, see where your group members are, etc. Okay? Any last minute questions before I stop the recording, divide you up into breakout rooms? Again, you don't have to stay long, just do a quick check-in, see how everything's working. Anything else? Math questions, logistical questions, anybody, anything else? Okay, let me get you divided up here. It's going to take me just a minute because I have to do this manually. And then again, sign out when you're done. I will see you guys tomorrow, and feel free to drop in for virtual office hours this afternoon if you need to.